Alright, so previously we have talked about polynomial functions. And next, let's have a look at rational functions. A function f(x) is called rational function if and only if it can be written in this form. f(x) equals px over qx, where px and qx are polynomial functions. And of course, qx is not a zero function, otherwise you have a denominator 0. It's not defined. And for example, all of these following functions, f(x) equals 1 over x, or 2x plus 3 over 6x plus 5, or the reciprocal of a quadratic function, all of these are called rational functions. So according to the definition of rational functions, we might have indefinite number of indefinite number of types of rational functions. In this course, we'll focus only on a rational function of this type, which is a quotient between two linear functions. Because we could easily see that this type of function, the graph of this type of function, can be obtained by transforming the function y equals 1 over x. So this function is of a relatively easy type, right? Because suppose you have a function f(x) which is a ratio between two linear functions, then in order to see the relationship between f(x) equals ax plus b over cx plus d and the base function gx equals 1 over x, we can actually transform this function like this. So first of all, we need to cancel the x in the numerator position. So suppose we have a cx plus d here. Note that we don't have a cx plus d, so we need to compensate that by adding a over c here. That way we have a ax plus ad over c, so we need to subtract it by ad over c. Then copy the rest of the expression there, divided by cx plus d, right? And then we have a over c minus ad over c plus bc over c over cx plus d. So this will give us negative ad plus bc over c times 1 over cx plus d, then plus a over c, right? So according to function transformation theory, we can transform that further to this c times x plus d over c plus a over c, right? So according to function transformation theory, we know that this is actually your coefficient a, and this is k, this is d equals well, let's call it uppercase d because we already have d here. This is a, k, d, and c, right? D equals negative lowercase d over c. So basically you add a 4-parameter to the base function gx equals 1 over x. So the graph of f(x) can be obtained by transforming the base function 1 over x. So the graph of f(x) will also have a shape like this, but probably with different x and y asymptote. It could either have two branches lie on the first and third region, or the second and fourth region divided by the two asymptotes, right? So next, actually, we can use a simplified method to decide whether you will have a graph like this or this. So let's use an example to illustrate the method. Make sure you can sketch the graph of such function very quickly. So let's suppose we have an example like this. sketch the graph of the function gx equals 2x minus 10 over 4x plus 10. So first of all, usually we'll simplify that function first. So gx equals, apparently we can put a common factor 2 in front, and 2 times x plus we have another 2x plus 5, right? So first of all, the function can be simplified to gx equals x minus 5 over 2x plus 5, right? Can you follow me?
Yep.
Next, let's find its horizontal asymptote and vertical asymptote. So first of all, vertical asymptote, which means the value that x cannot be. Apparently that's x equals negative 5 over 2, right? This line is its vertical asymptote. Which is somewhere, let's say somewhere here. Negative 5 over 2. Can you follow me? This is vertical asymptote because x cannot be negative 5 over 2. And then we can find this, vertical asymptote should be VA. Find its vertical asymptote, and then let's find its horizontal asymptote, which is the value that gx cannot be. So gx equals x minus 5 over 2x, right? 2x plus 5, right? You can consider the horizontal asymptote like this. Suppose we don't consider minus 5 and plus 5 here. Let's only consider this ratio. The ratio between x over 2x. When x approaches to positive infinity is just 1 over 2, right? And again, when x approaches negative infinity, it will also be 1 over 2. Because negative 5 and plus 5 compared to x approaches either to positive or negative infinity can be ignored, right? But the value can never reach 1 over 2 because the ratio between x over 2x is 1 over 2, but here you have x minus 5 and 2x plus 5. Therefore, the ratio between these two numbers can never reach 1 over 2. But it's very close to 1 over 2, right? So its vertical asymptote can be represented by this line. Y equals 1 over 2, which is basically the ratio between the leading coefficients here. Okay, also let's mark this on the 2D Cartesian plane. 1 over 2 is probably here. Again, not necessarily to scale. So that value is 1 over 2. So these are the two asymptotes of this function, right? And that means the function could either lie in these two regions or these two regions, right? Next, let's check which is the correct case. So we can examine its x and y intercepts. So next, let's find its y-intercept at first, because this is relatively easy. You can just simply let x equal 0, right? If we let x equal 0, we can see y equals negative 5 over plus 5, which is negative 1. So its y-intercept is just the point 0, negative 1. And you can mark this point here. That means the function must cross this point, right? And then let's find its x-intercept, which means we let y equal 0 and find x. If y equals 0, x must equal 5, right? So its x-intercept is here. So that means the function must cross these 2 points, which means you must have a branch like this, right? Which lies in the false region separated by the 2 asymptotes. And according to the point symmetry, the other branch must lie in the second region divided by the 2 asymptotes, like this. So in this way, we can quickly sketch the graph of such a function. Can you see that? again, we can put the expression of this function next to its curve. Okay, any questions? Okay, so next let's have a look at the nicer writing of the solutions. So first step is always to simplify this function. Gx equals x minus 5 over 2x plus 5, right? And then you can find its vertical asymptote and horizontal asymptote in this way. And mark these two lines in the 2D Cartesian plane. The next, you need to decide where are the two branches by examining its x-intercept and y-intercept. So apparently, one branch will cross these 2 points. So one branch must lie on this region, right? And the other branch can be easily determined according to point symmetry with this point here. And eventually, we can sketch the graph of such a ratio between two linear functions like this. Did you get it? Okay, next, let's have a look at some related concept, which is to solve rational equations algebraically. Suppose you have a rational equation like this, px over qx equals 0. How do we solve that? You could either use the first method, which means px must equal 0, right? And qx cannot be 0. Or you could also use the second method. Suppose you have a rational equations like this. We can use cross product. This is equivalent to AD equals BC, as long as x belongs to the domain. Okay, you see that? Or you could also rewrite this to a over b minus c over d equals 0. And this is equivalent to rewrite this using common denominator, ad minus bc equals 0. And this is equivalent to ad minus bc must equal 0, and bd cannot be 0, right? Be careful, always use equivalent transformations. The domain should not be changed. Okay, let's see an example to illustrate this concept. Can you solve this rational equation? On both sides, we have rational expressions, right? Can you solve this rational equation? I'll give you 2 minutes to consider this, and we'll have a look at the solution together. Okay, let's have a look at the solution together. So first of all, let's transform both sides in a vectored form. So the left side equal x minus 5 over x minus 4 times x plus 1, right? The right side is 3x plus 2 over x squared minus 1, which is x plus 1 times x minus 1. Right? So next, we need to ensure both of the two denominators cannot be 0. So x cannot be 4, and x cannot be negative 1, x cannot be positive 1, right? So as long as it ensures this, we can safely cancel the x plus 1 here. Then that's equivalent to x minus 5 over x minus 4 equals 3x plus 2 over x minus 1, right? And that's equivalent to, first, again, we ensure x cannot be 4, x cannot be either positive or negative 1. Then the second expression is equivalent to x minus 5 times x minus 1 equals 3x plus 2 times x minus 4, right? Also note that if you use cross product, do not forget to constrain your x here. Otherwise, if you don't consider this expression is not equivalent to this expression itself, right? Because in the second expression, x can be 1, but in the first expression here, x cannot be 1, right? So you do not forget this. This is very important. You have to constrain x in the correct domain. As long as you ensure the constraints here, then you can safely use the cross product. Did you get it? And that is equivalent to, first x cannot be 4, x cannot be either negative or positive 1. Then we can expand the cross product, which is x squared minus 6x plus 5 equals 3x squared minus 10x minus 8, right? And that's equivalent to, first x cannot be 4, x cannot be positive or negative 1. Simplify the second expression. 2x squared minus 4x minus 13 equals 0. Then you can try to solve this. This is actually a quadratic equation. We already know how to solve it, right? So let's call it star. Okay, so from star we can solve x is actually, we can just directly use quadratic formula to solve it. And that'll give you x equals 2 plus or minus square root of 30 over 2, right? In either case, x cannot be 4 and x cannot be either positive or negative 1. Therefore, the final solution is x equals 2 plus or minus square root 30 over 2. So this is your final solution. You get it? Okay, so next let's have a look at how we can solve a rational inequalities algebraically. So basically speaking, there are 4 types of rational inequalities. Either you could have px over qx greater than 0 or less than 0, right? Or px over qx is greater than or less than or equal to, greater than or equal to, or less than or equal to 0. So in the first 2 types, basically if you have a quotient that is greater than 0 or less than 0, this is equivalent to the sign in front of px and qx must be the same or different, right? You follow me? Or you could write it like this. This is equivalent to, the quotient is greater than 0 means the product is greater than 0. These 2 expressions are actually equivalent, right? For the second one, if the quotient is less than 0, this is equivalent to the product must be less than 0, right? And in the third case, if you have a ratio that is greater than or equal to 0, this is equivalent to 2 things. Whether the quotient is 0 or the quotient is greater than 0. And then you need to solve each of the function and inequality separately. And same thing for type 4. Again, always use equivalent transformation. Do not change the solution before and after the transformation. Okay, again, let's see an example to illustrate this concept. Can you solve a polynomial inequality like this? 4 over x minus 5 less than 3 over x plus 4. Alright, let's have a look at the solution together. So first of all, we can put everything on one side, right? And the original inequality is equivalent to 4 over x minus 5 minus 3 over x plus 4 is less than 0. And then we can rewrite the expression on the left side using common denominator, which is x minus 5 times x plus 4, right? And then 4 times x plus 4 minus 3 times x minus 5. This is less than 0. And this is equivalent to, we have basically 4x plus 16 minus 3x plus 15 over x minus 5 times x plus 4 must be less than 0, right? And simplify that to x plus 31 over x minus 5 times x plus 4 must be less than 0. So basically you have a quotient less than 0. This is equivalent to the product of these 2 expressions must be less than 0, right? Which means x plus 31 times x minus 5 times x plus 4 must be less than 0, right? And the left side is actually a polynomial function. Can you see that? So you need to study the corresponding polynomial function. It's better to sketch its graph. So next, let's study y equals x plus 31 times x minus 5 times x plus 4. Well, in order to sketch this graph, we need to study its degree, which is 3, right? Leading coefficient, 1 by 1 by 1 is 1, right? Which is greater than 0. So we know the end behavior of such a polynomial function is extending from the third quadrant to the first quadrant, right? Then let's find its zeros with orders to decide its behavior in the middle. Zeros with orders, which are x equals negative 31 with order 1, so I'll just put 1 here, okay? And x equals 5 with order 1, x equals negative 4 with order 1, right? So let's mark them on the number axis. Again, not necessarily to scale. It's just a schematic diagram. So each with order 1, that means the function will cross the first 0, then cross the second 0, cross the third 0, and connects to its end behavior like this, right? You get it? And your task is to find any interval such that this function is less than 0. And from this graph, we know that is this interval here and this interval here. Do not include the endpoints. Okay, therefore you can make the conclusion. The solution is x is either less than negative 31 or x is between negative 4 and positive 5, right? This is your solution to the original inequality. See that?